My name is Evan Allen. I'm from Virginia Tech, and my research today is on the feasibility of doing message authentication in automotive Ethernet networks really fast. So, as background, over the last decade, cars have become much more complex with many more electronic control units, or ECUs, inside. Makes them much smarter, but also much more vulnerable. And so a big issue is that in-vehicle networks, or IVNs, such as CAN, FlexRay, or Automotive Ethernet, have no standard way to authenticate messages. And that's bad because that means that malicious ECUs can spoof messages from other ECUs. So like one ECU could send a message like hit the brakes when it should never send that message. So we need some way for an ECU to be able to verify the integrity and the source of a message. So as an example, take this architecture here. This is a domain-based architecture where all the ECUs are connected with Automotive Ethernet. And each ECU has maybe like a CAN network of its sensors and actuators in the back. And in this example, a hacker has compromised either ECU 1 or 2 in the bottom and wants to send a message like brake to the target ECU on the left side. But neither of those compromised ECUs are the anti-lock brake system, or ABS. So this would be a case of message spoofing. And without any message authentication, the target ECU has no way to know that message did not actually come from the ABS. So that's why we need it. How do we authenticate messages? Well, a very common solution from IT is a message authentication code, which is a cryptographic tag that you put at the end of a message, and you can use it to verify the source. But this takes time to compute and verify. And in cars, we don't always have that time. The requirements for data vary dramatically depending on the kind of data, but it can be as low as 0.1 millisecond for latency and up to 100 megabits per second in throughput. And so when you combine multiple data classes, sometimes you have very, very little time to do these calculations. So the question is it even possible to do MAC authentication at these speeds? So that's what this research is about. And we did a review of the field, and essentially what we found is we could not find any papers that used a software implementation that could meet these most stringent requirements. We did find a paper that used MACsec in a hardware FPGA implementation that was able to meet it. But to investigate why the software couldn't get that fast, we profiled one recent proposal called Gatekeeper that uses a central authenticator and has all of its ECUs in a sort of star topology around that central authenticator. So we reproduced the results and we profiled each part of it. And we got this graph where each line here is a step of like the process to send a packet. And what we found was that it was not able to meet 0.1 milliseconds. But even if you take out the white parts in the middle, which are the software switching delay from the testbed, the authentication is just still too slow. And this is actually a pretty fast proposal compared to other work. We also noticed that in their paper, they noticed that on their development board, their hashing and encryption functions were just not fast enough. So the idea is like, how could any security protocol be fast enough if they're based off of these things? So what we decided was it's probably only possible to meet these most stringent performance requirements with dedicated hardware. Software just isn't fast enough. And it gets expensive to implement hardware cryptography on every single ECU. So while software methods might still be very useful for other use cases like ultrasonic data that don't need to be as fast, we still need a solution for very low latency and high throughput data. So one idea is maybe we can reduce the need for cryptography. So can we authenticate without crypto? One idea would be to use hardware ports. So this is normally a really bad idea in IT networks that are very dynamic and changing, but vehicle networks are much more static. So if we have an architecture like this where ECUs don't share a common bus, maybe we can authenticate that way. And this will assume that there's no physical man in the middle and that we can trust the domain controller, which we'll talk about later. But the idea is that if the ECUs each have one connection outwards, then they can trust that any data coming in is from the domain controller, and the domain controller can trust that any data coming in on a certain interface is really from that ECU, because physically there's nowhere else it could go. And so this means that using that part alone, we can sort of authenticate intra-domain traffic, and then for inter-domain traffic, now it might become more cost feasible to start putting in these hardware cryptography implementations for only a few domain controllers. And the end result is that the DC knows the actual sender and receiver of all the traffic. And so now we can start stopping like message spoofing and things. So for example, we can define a security policy where we say what each ECU is allowed to send and receive. And then we can actually block traffic violating these rules, kind of like a firewall. And in all of this, the ECUs do no work. So as long as the DC isn't compromised, it can stop malicious messages coming from an ECU that shouldn't be sending it, like an ECU sending a break message that's not the ABS. Of course, this does assume that the DC is not compromised, which is a big limitation, and no physical man in the middle. But in the future, we'd like to see if we can make these things better. How can we satisfy those performance requirements? How restrictive can those policies be? And how much overhead do they cause? And we'd also like to see if we could reproduce the MaxSec result. So, thank you.